Welcome to this fascinating exploration of the Droplet Memory Effect, a phenomenon where tiny liquid droplets remember their past experiences as they flow through microfluidic channels. Let's start with a paradox. In classical fluid mechanics, we assume that the behavior of a fluid element depends only on its current conditions, like velocity, pressure, and temperature. But droplets seem to break this rule. When a droplet passes through a junction or experiences a breakup event, it somehow retains information about that past geometry. Even when downstream conditions are identical, droplets with different histories behave differently. This challenges the classical assumption that fluids are memoryless. How can a simple droplet remember its past? Let's dive deep into the physics. Before we understand memory, we need to understand what these droplets actually are. In microfluidic systems, we typically have water droplets suspended in an oil carrier fluid. These droplets are incredibly small, typically 10 to 500 micrometers in diameter. That's smaller than the width of a human hair. The interface between water and oil is stabilized by surfactant molecules. These surfactants are amphiphilic, meaning one end likes water and the other likes oil. Now let's examine what happens at a microfluidic junction, the birthplace of droplet memory. Imagine a droplet approaching a T-junction. As it enters, the droplet must squeeze through a constriction. This causes significant deformation of its shape. Let's ask ourselves, what forces are acting on this droplet as it deforms? There are several key forces at play. First, surface tension tries to minimize the droplet's surface area. This is why droplets naturally form spheres, which have the minimum surface area for a given volume. Second, viscous forces from the flowing carrier fluid push and drag the droplet, causing it to deform from its spherical shape. To understand when memory effects become important, we need to introduce the capillary number, a dimensionless parameter that characterizes the competition between viscous forces and surface tension. The capillary number is defined as mu over gamma, where mu is the dynamic viscosity of the carrier fluid, u is the characteristic velocity, and gamma is the interfacial tension. Mu represents the viscosity. Think of honey versus water. Honey has high viscosity, water has low viscosity. U is the characteristic velocity, typically the average flow speed through the microfluidic channel. Gamma is the interfacial tension, the energy cost to create new interface area between the water and oil phases. Let's plug in some real numbers to see what capillary numbers look like in practice. For a typical oil carrier fluid, the viscosity is about 0.001 pascal seconds, similar to water. A typical flow velocity in microfluidics is 1 centimeter per second, or 0.01 meters per second. With surfactants present, the interfacial tension is typically around 0.01 newtons per meter. Calculating the capillary number, 0.001 times 0.01 divided by 0.01 gives us a capillary number of 0.001. This is quite small. When the capillary number is much less than 1, surface tension dominates over viscous forces. The droplet strongly resists deformation and quickly relaxes back to a sphere. When the capillary number is much greater than 1, viscous forces dominate. The droplet is easily deformed and takes a long time to relax. Now we can understand the mechanism behind droplet memory. It's all about the timescales of relaxation and the redistribution of surfactants. When a droplet squeezes through a junction, it gets stretched. During this stretching, surfactant molecules are redistributed unevenly across the interface. Before deformation, surfactants are uniformly distributed around the droplet interface, shown here as yellow dots evenly spaced. During stretching, surfactants accumulate at the tips where the interface is expanding and become depleted in the middle regions where the interface is compressed. Here's a critical question. How long does it take for the surfactants to redistribute and return to a uniform concentration? The time for surfactants to relax back to equilibrium depends on their diffusion coefficient and the droplet size. The surfactant relaxation time is approximately r squared over d sub s, where r is the droplet radius and d sub s is the surface diffusion coefficient of the surfactant. For typical surfactants, the surface diffusion coefficient is around 10 to the minus 10 square meters per second. For a droplet radius of 50 micrometers, that's 5 times 10 to the minus 5 meters. The relaxation time is 5 times 10 to the minus 5 squared, divided by 10 to the minus 10, which gives us 25 seconds. 25 seconds is actually quite long in the context of microfluidics. If the droplet travels through downstream features in less than 25 seconds, it still carries the memory of its previous deformation. The non-uniform surfactant distribution creates gradients in interfacial tension, which leads to the Marangoni effect. When we have gradients in interfacial tension, the del operator acting on gamma is not equal to 0. These gradients in interfacial tension create flows along the droplet interface, from regions of low tension to regions of high tension. These Marangoni flows create internal circulation patterns within the droplet that persist long after the initial deformation event. So how does this memory actually manifest in observable ways? Let's look at specific examples. Imagine two identical droplets approaching a second T-junction. One has just passed through an upstream junction 5 seconds ago, the other passed through 30 seconds ago. The droplet with recent memory has non-uniform surfactant coverage and takes longer to break up. The fully relaxed droplet breaks more readily. Droplets with memory can travel at slightly different velocities, even in identical flow conditions, because the internal Marangoni flows affect the drag forces. The droplet velocity is the sum of the imposed flow velocity plus a correction term from Marangoni-induced flows. These velocity differences are typically small, around 1 to 5%, but they're measurable and can accumulate over long channel lengths. Another aspect of memory involves pressure differences across the droplet interface, governed by the Young-Laplace equation. The pressure jump across a curved interface equals gamma times the sum of 1 over R1 plus 1 over R2, where R1 and R2 are the principal radii of curvature. For a perfect sphere, both radii are equal, so the pressure jump simplifies to 2 gamma over R. But for a deformed droplet where R1 does not equal R2, we have spatial variations in pressure that drive internal flows. Let me give you an analogy. Imagine squeezing a rubber ball and then releasing it. Initially, the ball is perfectly round and relaxed. You squeeze it into an ellipse. The rubber stores elastic energy in this deformed state. When you release it, the ball doesn't instantly return to a sphere. It oscillates and gradually dissipates energy. During this relaxation period, the ball remembers it was compressed. Droplets behave similarly. The surfactant redistribution and internal flows take time to dissipate, creating a memory window. Here's another analogy. When you stir your coffee and then stop, the liquid continues to swirl for many seconds, gradually slowing down due to viscosity. That swirling motion is the coffee's memory of your stirring action. It persists because viscous dissipation takes time. The internal flows within a droplet, driven by Marangoni effects, are exactly like this persistent swirl. They gradually decay, but persist for seconds to tens of seconds. To quantify when memory effects are important, we introduce another dimensionless number, the Pecklet number for surfactant transport. The surfactant Pecklet number is UL over D sub S, where U is the flow velocity, L is a characteristic length, and D sub S is the surfactant diffusion coefficient. When the Pecklet number is much greater than 1, convective transport of surfactants dominates over diffusive relaxation. Memory effects are strong. When the Pecklet number is much less than 1, diffusion quickly smooths out any surfactant gradients. Memory effects are weak. For typical microfluidic parameters with velocity 1 cm per second and channel length 100 micrometers, we get a Pecklet number of 10,000. This is huge, indicating strong memory effects. Experiments have beautifully demonstrated these memory effects. Let me describe a classic experiment. When droplets are generated with precise timing, they form uniform trains. But when generation is irregular, downstream spacing becomes erratic because each droplet carries different memory. This raises an interesting question. Can we intentionally erase droplet memory? One method is simply to wait. Include a long straight channel section where droplets can fully relax before reaching critical junctions. Another method is to use excess surfactant. When surfactant concentration is very high, diffusion from the bulk replenishes interface gradients quickly. Advanced methods include applying thermal pulses or acoustic waves to accelerate interfacial mixing and erase memory. Understanding droplet memory has important practical applications. In drug delivery applications, droplet memory affects how uniformly drugs or nanoparticles are encapsulated within droplets. For chemical reactions in droplets, memory affects internal mixing patterns and thus reaction kinetics. In digital microfluidic computing, where droplets represent information bits, memory can create errors if not properly accounted for. For those interested in the complete mathematical framework, let me show you the governing equations. The incompressibility condition, divergence of velocity, is 0. The Navier-Stokes equation for the fluid momentum, the surfactant transport equation on the interface, where gamma is the surfactant concentration, U sub s is the interfacial velocity, and del sub s is the surface gradient operator. The equation of state relating interfacial tension to surfactant concentration, where gamma naught is the clean interface tension and gamma infinity is the maximum packing. These equations are coupled and highly nonlinear, which is why numerical simulations are essential for detailed predictions. The droplet memory effect forces us to rethink some fundamental assumptions in multi-phase flow theory. Classical theory assumes local thermodynamic equilibrium, meaning interfaces instantly reach their equilibrium state. But droplet memory shows us that interfaces can remain far from equilibrium for extended periods in microfluidic flows. This suggests we need new constitutive relations that include history dependence, not just instantaneous local conditions. For engineers designing microfluidic devices, here are key principles to consider. First, always calculate the surfactant relaxation time for your specific system. This tells you how long memory lasts. Second, compare the relaxation time with the residence time in your channels. If residence time is shorter than relaxation time, memory will be significant. Third, either design devices that allow sufficient relaxation or exploit memory effects intentionally for sorting or control. Despite significant progress, many questions remain open in droplet memory research. How does memory affect the coalescence or repulsion between nearby droplets? This is largely unexplored. Can we exploit memory as a form of information storage in lab-on-chip devices? This could enable new computational paradigms. In biological systems like cells, do similar memory effects exist in membrane deformation? This could have implications for understanding cellular mechanotransduction. Let me summarize the key concepts we've explored. Droplets remember their past through non-uniform surfactant distributions that take time to relax. The memory timescale is set by surfactant diffusion and is typically on the order of seconds for microfluidic droplets. Memory manifests as internal Marangoni flows and pressure gradients that alter droplet dynamics. The capillary number and surfactant Pecklet number tell us when memory effects are significant. Understanding and controlling memory is crucial for reliable operation of microfluidic devices in chemistry, biology, and medicine. Finally, let's reflect on the broader significance of droplet memory. The droplet memory effect challenges the classical notion that simple fluids are completely memoryless systems. It reveals that even a tiny droplet of water in oil harbors surprising complexity when we look at the right timescales and length scales. Most importantly, it beautifully illustrates how molecular scale physics, like surfactant diffusion, can have measurable macroscopic consequences.